The diameter of the network. That's the longest, shortest path between two nodes in the graph. That would be.
Data table.
What?
Data table. There is a table called data table.
Yeah.
And there we can.
Yeah. Then we are in Gephi.
Yeah.
If we should explain it outside Gephi just by here, what would be the rules for computing the clustering coefficient if you had to do that?
The actual amount of connections between friends divided by the possible amount of connections.
Yeah.
Friends, yeah.
So the actual connection between friends divided by the possible. So here we have. So we can find out that if we start here, we can say we have 1, 2, 3, 4, 5, 6 friends. Isn't that? No, 7. That's what. 1, 2, 3, 4, 5, 6, 7. 7. So it's 7 times 6 divided by 2. So that's 21. Isn't it?
So we have to count the number of friends of Mats.
Yeah, and then we can look at. Of course, we could use Gephi, but just to wrap of what we talked about last time. So, what are the friendship between friends here? Is there actually any?
No.
No. So that's an easy. That's easy.
Yeah.
Compute. None. Yeah. 0. Because there's no. So there's none of the friends here that are actually direct connected. So of course there's connection here, but they are not friends directly. So that's easy. So we didn't even have to make the calculation anyway. But anyway, if we have found anything, we have just taking that divided by the n times n minus 1 divided by 2, and then that will be the coefficient. And the higher number, the more likely that part of the graph will form a group, an interconnected group. So that's the what is the degree of this egocentric network? What?
Using Gephi?
Yeah, but we didn't talk last time about a way to use Gephi to do that, to solve that. So yeah, you could use Gephi to solve this one, of course, and this one also, but not this one, except if you use the filtering and. So what is the degree?
Isn't it 8? 3, right?
A 3 degree.
Isn't that the amount of edges connected to the node, or?
If you look at the network, the first degree is looking at all the friends of Mads Mikkelsen. They are here, and then that's the first degree. If you go to the second degree, that's all the friends of Mads Mikkelsen's friends. So that would be the one that are friends with one of Mads Mikkelsen's friends, and then the next degree will be the friends of the friends of the friends, and so on. So you just have to look like that, and then you find out that
it's 2.5, right?
No, 2.5. So 2.5 means that you have. That will be you go to have friends and you have friend of friends, and they are connected. That will be 2.5. So look, we saw that there was none of the direct friends that were connected. So we can go to the next level. So that's the ones that are friends with the friends. So we are on this level here, and this level, and this level, and this level, this level. So we can see if any of them are friends. That will they'll move us to the 2.5 degree. But what we can look for is to see if there's anybody further away. So that would be this guy over here. So there'll be 3, and no matter how. So you have to look at the shortest path from the ego to, and that would be 3. You cannot get here with fewer than 3 nodes. So we get to at least the third degree here. if we should go to 3.5 degree, then you should find another one or other ones that are in 3rd degree, and they should be connected. So that's not the case. So it's a 3rd degree network. This one.
And how do you find the diameter of the network? You just find the longest
yeah,
on the bus?
Of course, if it's in this size, you could do it by hand, but just finding what could be the possible longest pad in the network.
The longest path is the diameter, right?
Yeah, the longest, shortest path. So not the longest possible path you can take, but the longest, shortest path between two nodes. And I think, what is it? What did you compute it in Gefi? What?
I don't get
5.66.
6?
Yeah.
So we go here, 1, 2, 3, 4, 5, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, yeah, something. But as you can see, as soon as it gets just this size here, it becomes difficult to figure out by just looking at it. So we need some tools.
I'm sorry, I don't get it. What's the shortest path? What's the longest shortest path? I don't get it.
The shortest part is just the shortest possible connection between two nodes.
Mm-hmm.
And if you look at all the shortest possible, if you look at the path between all the nodes in the tree or in the graph, so take all possible paths and look for the shortest path between all of them, and then you find the longest of them. That's the diameter. So if you look, for instance, you can say, so from here you can have 1, 2, 3, 4, 5, 7. That's a path between Sean Connery or Mads Mikkelsen, but it's not the shortest.
Yeah. Okay.
Because this is the shortest path is here. So that's not interesting. So
But it's a path with who and who?
anyone.
Anyone?
Yeah. So when we talk about the diameter of the graph, it's the longest possible distance you can travel if you are traveling along the shortest path between the nodes in the graph. Yeah.
When you talk about in degrees and out degrees, is that in directional networks only?
Yeah. It is. And of course, it influences because it's like traveling on a one-way road, so that makes a difference for the path, because you cannot go in both directions necessarily. So that will make a difference.
So in this case, it's totally impossible to do that by hand, right? It's tricky.
No,
Because you have to compute every path between every single point, right?
Yeah.
So I want to know the path between Sean Connery and Robert De Niro.
Yeah, but you can exclude a lot of them because you know that this is here's the path. The distance of this is 3, so you know the longest, shortest path must at least be 3. So there's you don't need to look at all these ones, because they will never be part of the longest one. And so in that sense you can somehow exclude a lot of, so you don't need to take all possible pairs of all possible combinations, because of course that's not possible but you can start excluding
Okay, right. Fine.
yeah.
I
So
understood.
somehow you can figure out what.
So-
you need to see when it's laid out like this. You know that you have to find something that are in the surface of the.
So here the answer is 6, right?
Yeah.
So it could be the distance between Sean Connery and Robert De Niro, right?
No,
Yeah, Sean Connery, Stellan Skarsgård.
no, it cannot be that,
No?
because it needs to be the shortest path. And the shortest path between Robert De Niro and Sean Connery is 1.
Oh. So it could be between Sean Connery. Oh.
Always need to be the shortest one. So you can just exclude all the other ones. So
Okay.
so you will never be this one because that the shortest part between these two is,
Okay,
is
all right.
always one. No matter how many other parts you can find, it will always be the shortest will always be one here.
Okay, fine.
So I think 1, 2, 3, 4, 5.
What?
So-
Well, it's very complicated to do that by hand, I think.
Yeah, is it
Not
is it 5? But anyway, Giphy can compute that for you. So the principle is find the longest part, and of course, in a graph that have more than, this is I don't know how many 20 nodes, it becomes very difficult. Depending on also on the layout, because the layout can be very confusing also. So you need tools for the help. Did you have a question?
If you calculate one as 16, like a degree 16 for maths, Michael, yeah,
The degree of 16
yeah,
degree. What degree?
it's just a degree, like,
What?
it's just a degree,
Just a degree?
yeah. How is it?
I don't know. I will look to that into that because the degree here will be 3 because that's the from an egocentric network it will be 3. That's the you only have friends of friends of friends and they are not connected. That's the. What about the? Yeah, the next one is pretty simple. It's not that.
So the density of the graph is again computable by the Giphy.
Yeah, the density of the graph is computed by the number of edges compared to the number of possible edges. That's the density. So how connected are the graph? How many connections are there? So that's the density. What is the highest possible coefficient in the graph? 1. Yeah. Yeah, because it's everybody is connected, so makes sense. So how many numbers of edges are in the graph? What? 28. Yeah, so it must be 9 times 8 divided by 2 minus 1.
Okay.
Oh, yes.
9. That's 72.
50.
50. Yeah.
Yeah.
Probably it's 9 times 8. That's the 72. Divided by that would be 36 minus 1.
35.
35. Did you get that?
I did.
Number of edges, you can just count.
No, you cannot count because you don't know. You don't have to. Yeah, you could of course.
Okay.
Because
Yeah, you can draw it, but
it's on directed line, so we need to like take care of, like if A is connected to B, the edge will be A to B and B to A also.
no, it's an undirected complete graph. So yeah. So if there's only one line between each pair of nodes,
Yeah.
that's why we have to divide it by 2. We talked last time about how many handshake can you do in a room. If you are entering the room, you can if you don't make a handshake to yourself, you can make a handshake to everybody else. That's the number of people in the room minus 1 yourself. That's the number of everybody can do that. Everybody in the room can do that. So that would be the number of people in the room times the number of people minus 1, because that's the number of handshakes everybody can do. But then everybody will have made handshake in both directions. I will have made a handshake to all other people, and all other people will have made handshakes to me. That means that that we have done it twice, and so we can. If we only should do it once, we can take away half of them, and so that means that the number of nodes times the number of nodes minus 1 divided by 2. And if you have 9 nodes, you have 9 times 8 divided by 2. That was 36. And then if you remove one of them, you have 35 edges left. It's just a random one. Yeah. Yeah. It's not because it needs to be a math class, but it's just the definition of. So what about the song contest? Did you manage to visualize that? With the what?
No.
So see if I can. Do I have it open?
I just expect.
So it starts out like this when you open it in Gigi. So the first thing that you want to do is somehow to lay it out in some way. So choose a layout. I don't know which one. If you just choose this one, that's probably not a good one. Let's take another one, this one, and then do something like this. No, still not good.
You might.
Let's try this one.
But you might change the distance, right?
No,
10,000.
So we have this one. Here we can try to see. So here we have the nodes. We want to lay it out in a nice way. Let's just do that. See. So now we have the layout here.
Maybe if you increase the repulsion strength.
What?
The repulsion strength might, if you increase that, it might look better.
Yeah, but this is isn't this fine?
Oh yeah, sure. But if you had like the edges as well.
Oh yeah, but if I add the edges, I can just
Yeah.
do like this. It's just because so this is okay. This is a graph that's okay. So I want to have the text also there because I want the names. So I just minimize them. So and then I just change the color of all the nodes. So the background color of the node. So now I can actually see all the nodes here. So that's okay. That's I want to do two things with this one. I want to color look for the groups inside. So I want to go into here and compute the modularity. So I compute that. I get four different groups, and then I want to color the nodes by that. So now I have, if I use the zoom here, it's absolutely easier with the mouse, but something like this. So let's. So here we have 4 groups. We have a group here. We have this purple group, and then we have the green one and the blue one. Can you answer the question that is there any region in this content that is more likely to vote on each other than others? Of course, you need to know how these countries are positioned on the map, but at least it looks like all the orange ones are Eastern Europe countries. There's also been this about the Nordic countries if they are voting on each other, but that's not the case because, at least in this one, because Sweden and Denmark are in the same group, but Norway are not in that group. So the only thing you can say is that it seems like this group is located in one specific area, and they are somehow grouped by this. But anyway,
Except for Latvia, I guess. Some reason. They're in the middle of everything.
what?
Latvia, I guess that's LBA.
Yeah,
They're in the middle of everything.
yeah. Of course, and if you wanted to say something about that, you probably need to look at more than one content. We want to see more than that. But anyway, it was just to give an example of something that you could look for. The next thing we want to do is to change the size of the nodes so we can see who are the winner of the content.
Oh, yes.
So we want to the edges are weighted with the degree, with the points that they are given. So we need the weighted degree. So I compute that, and then I choose the size and say I want to use the weighted degree, and then say okay, fine. I should be a little bit more here.
How did you use the size? I didn't see. Oh, yes. Okay, right.
So now the size is defining the weighted degree on the nodes. So you can see that Austria won and Holland was on the second place and Sweden on the third place. So, the example of using the information to get a fast view of the data. You could also reverse it. So you, if you wanted to see which one are the loser, so you can then you just do the opposite here. Say then we say 15 to the smallest one and 5 to the highest one, and then you can see that of course Austria will get the smallest, but it's very difficult to see a difference because only in the top you have they are separated, but when you get down in the numbers they are divided, so it doesn't give you any information from a visual point of view. So let's get back to the 5 and 15. So this is just some numbers that you have to work with. See what is the best possible sizes. It could be that it should be larger or smaller or whatever, depending on the.
France was not very good that time.
Yeah, no. Only I think half as good as Denmark in that. but anyway, this is an example of visualizing some data that you. So for instance, if you one way, of course from a scientific point of view, this was probably not that interesting. But if you want to do a presentation, if you want to give a talk about something, then this visualization could probably help you in doing that instead of trying to explain the same thing in words. So that could be the purpose here. Anyway, that was the exercise there. What about the last one here? Any ideas? Which one is connected to which one? Yeah?
I have a guess.
Yeah?
C is connected to 3.
To 3?
Yes, I assume that because in the third graph, the size of the nodes are quite similar.
So this is the degree. So
Yeah.
so that should at least this one should be small. We know that. So that makes sense, and it looks like it's okay. So if that's the degree, what about the two others? Any arguments for which one is what? So you can, what?
One is more on the more data ID side.
Yeah, but so if you have used the degree and say the degree is over here, let's just keep in that. Which one is then between this? Yeah,
I think it's 2.
2. Yeah, why?
Yeah, I can't.
But I agree on that. So why do you think that betweenness is number 2 here? What does the betweenness mean? So being between something is being on the shortest path between all nodes. Yeah.
Yeah, it seems that there's a bigger contrast between like all of these down there. They are
Yeah,
very
here.
small compared to the one in the middle.
Yeah, this one.
Yeah, and then it makes sense that the betweenness for those down there are very small, and
Yeah.
the one in the middle is very big.
Yeah, and the same. If you look here, we have these two being between these guys over here and the rest, and the same up here. We have at least these two being between this part of the graph and this part of the graph. Yeah, so that could be an argument for being between us.
There's also a single node in not the bottom but bottom right-ish,
Yeah.
that one, which is on network number 1. It is larger than some of the other values, which
Yeah.
would never happen in a betweenness.
No, it will never happen. Yeah. So that's also an argument that so what about this one should be the closeness then? So that means that
By default.
how central are the nodes to the other nodes? So the average of distance between one single node and all the other nodes in the graph. Yeah, so I think this is the closeness. So this is the one with the shortest distance to all the other nodes. Makes sense. It's if you look at the this is betweenness, and this is the degree. Yes. So that was the exercises from last time. I will have one more thing I want to discuss with you. That's the exam. Just before we start. Exam. Wow. I'm happy now. So I just made some these 3 slides here. So the deadlines. So the course is ending 3 weeks from now. The assignment handing is 5 days after the last course day, and the oral exam will be in the beginning of January. So what is this assignment? So the assignment should be a 5 to 10 page synopsis, and what you should do in that is you should select a use case. Could be a real one or something you just imagine. Yeah.
So we can use like whichever data set we want, maybe?
Yeah, absolutely. So that's not the no. So the idea is to try to bind all the different things we have talked about in this course to some use case, to find out what could be the use of the different elements in that specific use case. How could we benefit from that? What could be the business intelligence that could come out of? It's not necessary that all elements will contribute to that specific use case. That's fine. That's not a big problem. But of course, you have to find something where more than one actually is giving something to the